Hello everyone, welcome to Computer Science 227. In this lecture we'll be talking about binary search trees. Okay, we'll keep exploring that. We'll talk a bit more about that, and I want to keep these lectures, all of them short, to be under half an hour, such that it will be more convenient to you, will be more convenient to me recording wise and editing wise, and it will still be available on YouTube. You will still be able to watch it at any time you want. So binary search tree. Let's get back to the slides. So what is a tree? A tree is a data structure with the root value and subtrees of children with the parent node represented as a set of linked nodes. Again, so technically a tree can be something like this. Okay, so I have a node, I have like one child, second child, third child, let's say a fourth child, fifth child, okay? And then let's say, I don't know, this guy has two children only, okay, and that's it. Okay, and this guy has only two children, something like this. Okay, now yeah, so that will be a tree, and I guess the difference. So you may be thinking, what's the difference between the graph in computer science and the tree in computer science? So I don't think we probably didn't talk about graph yet, but graph would be kind of similar to that. The only difference is this data structure is hierarchical. Okay, it goes from top to bottom. It goes that way. Okay. These nodes are linked to each other. You can only go from parent to the child, not vice versa. You cannot go from a child to a parent. There are some deviations though. There are some classifications. There are some particular cases of binary trees, right, where you can go up one level up, but not in binary search tree. Anyway, so you have the trees. Okay, you have a tree like that. Now you can always go down like this from the root up until very bottom. So the nodes, the last nodes in the tree are called leaves. Okay. So binary tree is a hierarchical data structure where you either have an empty node. Okay. So it consists of one element or no elements. So that top node is called the root, and two distinct binary trees called the left subtree and the right subtree, either both of which may be empty. Okay, so the difference between this tree and the binary search tree, so binary tree, right? Binary tree is the idea is that you allow it to have at most two children. So this guy has two children. This guy also has, let's say, two children. This guy has only one child, and this guy also has, let's say, one child. Okay, so you allow it to have only at most two children. It's okay if you have one, it's okay if you have zero, right? So for example, this guy has 0 children, this guy has one child, this guy has 2 children, this guy has one child, this guy has no children, right? So basically you still have the connections, right? But they just point to nulls. So kind of like I'll draw axes, they point to nulls. Okay. So here's an example of a binary tree. So the tree doesn't have to be specifically a tree of numbers. They can be a tree of letters. Okay, the idea is still the same. You have at most 2 children. Okay, some definitions: length of a tree. So length of a path is the number of edges in the path. The depth of a node is the length from the length of a path from root to the node. The set of all nodes at a given depth is called a level. Siblings are the nodes that have the same parent. The root of the left or right subtree is called the left or right child. Node without the children is called the leaf. The height of an unempty tree is the length of the path from the root to the furthest leaf. Okay. Now, binary tree can be represented, if we try to implement that in Java, binary tree can be represented in as a set of linked nodes. Okay. So again, imagine this guy is linked to this one and that one. This one is linked to this one and this one. This one is linked to this one, and also linked to basically like empty link, which is null, right? This guy is like doesn't have anything below it, right? So it's linked to 2 nulls. Okay. So imagine you have a root which is 60. It's linked to 55 and 100. 55 is linked to 45 and 57. 100 is linked to 67, 107, and yeah. Okay, and so that is so-called binary search tree. And if you remember, binary search tree is a tree where all the nodes, if you take any node, let's say this 60, all the nodes on the left from that 60 will be less than 60, which is 55, 45, 57, and all the nodes greater than 60, 167 or 107, will be greater than 60. And that is true, that property is true for all the nodes. For example, if you take this 100, right? So all the nodes on the left from 100, which is 67, 60, 55, 57, 45, are less than 100, and 107 is will be on the right hand side from 100 and it's greater. Okay. Now we talked about how would we search. Okay, so again, imagine that in this particular case I'm searching for 107. So what should I do? I have only access to the 60. I only have access to the root. I start searching for 107 from 60. I'm comparing 107 to 60. Okay, 107 is greater than 60. What does that mean? That means all the nodes on the left from a 60 will be even less than 60, which means 107 is definitely not there. Basically, if 107 exists, it gotta exist somewhere on the right hand side. So from 60 I go to 100. Okay, is 100 is less than or greater than 107. 100 is less than 107. That means 107, if it exists, it's definitely not on the left. It's got to be somewhere on the right. And then I come to 107. I found it. That's it. Return true. Okay, I found it. That's cool. If, let's say, I'm searching for an element which doesn't exist there. Let's say I'm searching for 0. Okay, I'm coming here. 60. Is that less than 0, greater than 0? 0 is less than 60. That means if 0 exists, it gotta be existing somewhere on the left. Then you go to the left, 55. You're comparing 55 and 0. 0 is less than 55. Okay, so if 0 exists, right, at all, then it's gotta be somewhere on the left. Definitely not on the right. Okay, so basically, again, like you completely eliminate, you completely remove some portion of the tree every time you're making a comparison. Okay, so the first time you compare it, you basically remove the half, like the right half. Okay, then when you compare it to 55, you removed like that 57. Then you compare that to 45. Is 45 less than 0? 45 is greater than 0. Okay, so if 0 exists, they gotta exist on the left. And then you're trying to access the left child of 45, and you see that it's null. Okay, so there is nothing there. That means you're done. There is nowhere to search anymore, and that's why you should return false. Okay, so 0 does not exist in this tree. How you implement it? How do you do that? So that's how you create a class for the node. The book is using generics. We'll be just creating the class of binary search of integers. Tree node e left right tree node. Okay, so the element itself, left right, and the constructor. Now, how do you create a search? So here's the code. Let's talk about the code. Okay, maybe can I copy that over here? Can I? I thought view, edit, paste. Allow. No, I cannot. That would be so cool. No valid data on clipboard. Okay, anyway. So what do we have here? We're creating a current node, okay, tree node, so this guy, current node, and assigning that to root, right? Why? Because we always start searching from the top of the tree. We always start searching from the root. Okay. Again, so always start searching from here. We always start searching from over here. Okay. Then the idea is this: like you compare your nodes to you compare the element you're looking for, which is this element. You compare that to the current node, and then you make a decision if you should you go left or right. Okay, and then you just repeat that over and over and over again until you either found the element or until you encountered null, which means you just use stock. So like you went to the leaf and it, your element doesn't exist in the tree. So while current is not equal to null, what do? If element is less than current.element, which that means, so if something we're looking for example 0, right? We're comparing 0 and 60. If element 0 is less than 60, then what do? We go left. Okay, if element is less than current.element, we go left. Current is equal to current.left. Okay, so let me draw. So let's say at the very beginning, that's your element. Okay. Okay, so that's the element. Let's say 24. Okay. Okay, so that's the element, right? At the very beginning, the root is the element. Then we're comparing element and the current.element. Okay, so we're comparing this. So sorry, no. Hold on. Current, not the element. Current. Not the element, but the current. Okay, so current is the pointer. Current. Okay, so at the very beginning, current points to the root. Okay, then we compare current to the element that current. Okay, then it turns out that, for example, if element is less than current.element, then we go left. Okay, what does that mean? We're changing current to pointing not to the current but current.left. In other words, our current doesn't point to this element, it starts pointing to this element, which means this guy, we can erase this link, okay? So, and then again, we're comparing this element to this element to the element we're looking for. If the element we're looking for is less, then we also need to go to the left, okay? So basically the same thing. We're changing the link. We'll go over there. Okay. Current.left. So else if element is greater than current.element. Okay, so for example, let's imagine that we're looking for, I don't know, 57. We're comparing 6 to 57. 57 is less, we'll go to the left. We're comparing 55 to 57. 57 is greater, that means we need to go to the right. Okay, so that means we need to change current not to current.left but to current.right, which means that, for example, if in this case, okay, so let's imagine that I have a right child here. Okay, so if at this point I need to go to the right, what do? I just need to change the link to the right child. Okay, that's what I do. Okay, so I change the link from here to over here. And then that's kind of the whole idea. You start from the top, you either go left, right, compare the element to the node, go left or right, compare element to the node, go left or right, go left or right, go left or right, up until you either find the element or you found null. Okay, so that's the idea. So if element is less than current.element, then you go left. If element is greater than current.element, you go right. And now you see there is else. What does that mean? What does else mean? Else means that this is not true. Element is not less than current.element. This is not true. Element is not greater than current.element. So what's the only case left? The only case left is when element is equal to current.element. In this case, that means that we found the element we're looking for, and then we return true. Okay. So our search was successfully finished. Now, if, let's say, we just keep looping, okay, and we didn't return true, okay, then at some point we're going to exit the loop. What is the only condition under which you can exit the loop? It's only when current is equal to null. And when is current is equal to null? Current is equal to null, for example, for this tree I'm looking for 0. From 60 I go to the left, from 55 I go to the left, from 45 I go to the left, and then current, so for example, if I go over here, right? Okay, so I needed to go to the left, and then to the left, and then current is equal to null. Okay, so that means I was not able to find my element in this tree. So 0 is not in this tree, right? That's why I need to return false, and that's when you return false. So element is not in the tree. So that's that's how you implement search in binary search tree. Now, what other functions, what other things you can do with the tree? Another thing you can do is to insert an element in the binary search tree. So let's imagine that we have a binary search tree like this and we want to insert, let's say, 0. Okay, so you may be thinking, okay, so how would you do that? Maybe like you have 60, 55, 45, 57. So what if I do like 0? What if I make 0 to be the root? And then 45 will be greater than, so 45 will be on the right, then 55 will be on the right, then 57 will be on the right, then 60 will be on the right, then 67 will be on the right from 60, then 100 and 107, right? So that's a possibility, right? So basically you can create a tree like this. So 0, the one which you just inserted, then 45, right? Then what else? 55, 57, 55, then 57, then what? 60. Okay, and just create a tree like that. So basically 0 will be the root, and like it will go on and on, right? There'll be no left children because nothing is less than 0, and then the entire tree will be on the right. So yes, that is possible. Unfortunately, that's very, very inconvenient because you have to change the entire structure of the tree. You have to change all of those links, almost all of them, and that's very inefficient, right? You just want to add 0 to it. Like, you should not be needing to change the entire thing, like to relink all the elements. That's not efficient. Don't do that. That's why the rule is this: the new element always becomes a leaf. Always. So for example, if I want to insert 0 here, I definitely know that 0 will be over here somewhere among the leaves. Okay, so the easiest way to insert 0, to insert an element, is this. Basically, it's very similar to search. So basically, like, try to search for 0. If it doesn't exist, then insert it as a leaf. So basically do something like this. Compare 0 to 60. 0 is less than 60, go to the left. Compare 0 to 55, go to the left. Compare 45 to 0, go to the left. And then create a node over here and link 45 to 0. Okay, so for example, over here, if that's the tree, I compare my 0 to this guy, then this guy, then this guy, then this guy, and then at the very end, I insert my 0 over here. Okay. Yeah. So if whenever or for example, if let's say I want to create a node, insert a node which is like, I don't know, 68. Okay. So 68, what would that be located? Okay, so 60 is less than 68. That means 68 has to be somewhere on the right. Then 100 is greater than 68. That means 68 should be somewhere on the left. Then 67 is less than 68. That means 68 should be somewhere on the right, and then we're stuck, right? We encountered null. That means just create the new node 68 here and connect it to 67. Basically do it this way. This way, okay, and then just do this, and then connect it that way. Okay, hope it makes sense. So the new element always becomes a leaf. Need to preserve the main property of a binary search tree. The elements greater than the new element need to be on the left. Sorry, greater than they need to be on the right. Elements that are less, they need to be on the left. Starting from the root, compare the new element to the current node and do the same to its right or left child. Okay, I hope it makes sense. It's just, again, like exactly what I described. Exactly what I described. You start from the root, you always start from the root. So let's say, for example, here, I decide to insert, I don't know, let's say 50. Okay, 50 doesn't exist, so it's a valid number to insert. The idea is, so the first rule, my 50 definitely has to become the leaf, so it will be somewhere at the bottom, okay? And then after I insert 50, the main rule of the binary search tree has to preserve. It still has to be the same. Whatever element you take, all the elements less than that element should be on the left, all the elements greater than that should be on the right, okay? So that definitely has to be true. And yeah, so how do you do that? For example, if I want to insert 50, I compare my 60 to 50. 50 is less, that means it should be somewhere on the left. Compare 55 to 50. 50 is less, go to the left, 45 to 50, 50 is greater, go to the right, and right here, 50 will become the right child of 45. Okay, so as you can guess, in the homework, that's what I'll ask you to do. I'll ask you to write the code to actually implement it, how specifically it can be done with the code, and to test your program. So let's practice a couple of, well, I guess that's those are the steps how you would create that method. What I want you to do, I want you to create a class called binary search tree of integers, which would support insert int key method. Okay, so over here they were talking a binary search tree for a generic class. I mean, I don't care about generics. I want us to be limited to integers. That's okay for now. Otherwise, actually, this becomes tricky element. But anyway, so I'm kind of simplifying the task. So we need to have a node class. Okay, let's create a node class. It's going to look something like this: node int key, node left right, and public node key is equal to, yeah, and creating the constructor for the node. Node int item, key is equal to item, left, so like left is equal to right is equal to null, right? So basically, whenever we're creating a node, right? So not a tree, just a node. What do we do whenever we create a node? So whenever we create a node, we create the node, we assign the element, so the value, and then we create two links pointing to nulls, so the pointing to nothing. Okay. So do that first. Second, we need to have a constructor for the root variable. Okay. So root of binary search tree, node root constructor binary search tree root is equal to null. Okay. So now I want you to create a class which is called binary search tree. Okay, so that's basically the entire code I already provided for you for the node. Just copy paste that. Now, please create a class called binary search tree of integers. Okay, and then or binary search tree, but in this case, so constructor should be the name of the constructor should be changed. So node root binary search tree. When you're creating a binary search tree, right, so what's the most important thing is that you need to have the root initialized. When you're creating a completely empty binary search tree, which contains no elements, which contains no nodes, that means the root should be null. So the root should not exist. Kind of like the tree exists, but it doesn't contain any elements, not even the root. After that, when you do this, so here's kind of the code which you may use. Completely up to you. That's kind of like the help for you. This method mainly calls insert track. Okay, so we're going to do recursive call for the method which is going to insert an element in the tree. Avoid insert int key root is equal to insert track root key. Okay, so we're going to insert, and we're going to call the recursive method which will be inserting the node. Okay, so here you can see node insert track. Okay, which means that it's going to return a node. Okay, so that there is a method, it's going to do something, and then it's going to return a node, and yeah, so it's going to basically return a pointer, right, a reference to the node. So what do we do in this insert? If the tree is empty, how do you know that? If root is equal to null, okay, then you need to return a node. In other words, if the root is null and you're trying to insert a new node in it, what do you think should happen? If you insert something into a completely empty tree, then that new node which you're inserting should become the root. Okay, so write that's my hint, write the function here. Otherwise, you need to recur down the tree. So if key, okay, so if key is less than if, else if is greater than, okay, so like figure out what should happen here. Then return the unchanged node pointer. In other words, node pointer. Okay, yeah. Insert root. Yeah. So basically, you should insert a new. Yeah, you should insert a new element into this tree, and then you need to return. Then you need to return. Well, in this case it's not clear, but you can return either the pointer to the root. Okay. Well, I guess, but there is no, yeah. So there are two options: either return the pointer to the root, or return the pointer to the element you're creating, the node you're creating. Basically, this node root. Okay, so basically like this root. Completely up to you. But anyway, and well, actually, in fact, you don't have to return anything at all. Just make sure that you insert it in the right position. That's already like more advanced thing. Okay. And then what I want you to do, I want you create a method to print out a tree. Okay, so we'll do so-called in-order traversal. If you want to Google what that means, in-order traversal. But here's the code. Basically, what in-order traversal does, it traverses a tree, okay, and prints out the binary search tree in the way, like in the way of ascending nodes. Basically, it's going to, like for this, for example, binary search tree, it's going to print out 45 first, then 55, then 57, then 60, then 67, then 100, then 107. Okay, you don't have to understand how it works yet. Okay, we'll be talking about it a bit later. But yeah, so you can just copy this code. Okay, and then the main function, I want you to test the code. I want you to insert in the completely empty binary search tree 50, okay, so it becomes the root, then 30 goes to the left, then 20 goes to the left of 30, then 40 goes to the right of 40, then 70, then 60, then 80, and then print out, so call that method in order. Yeah, so that's what I want you to learn to do. That's it for today. I hope you guys enjoyed the class. That's a binary search tree. We'll be exploring more and more and more of that things in that data structure. Okay, we'll be talking about balancing that. In the Computer Science 318 class, we'll be talking about, like, for example, what happens. Hold on. I think next class we'll be actually talking about how to delete a node from the tree. So think about this. Let's say you have this binary search tree, and let's say you decide to delete 50. How would you do that? That's a question, right? Because, I mean, well, in this case, it's maybe kind of obvious. You either make 45, right? That 55, you kind of like shift this one up, or you make 57 and shift, like move one position up. The problem, though, for example, what if there were some elements below? For example, what if you decide to delete 60? What happens? Okay, so that's not really like clear. For example, if you decide to move 55 up, right, then okay, 100 will be on the right from 55, but here we have two children. So which one of them will become the left child of 55, and which, for example, 45 will be on the left from 55? What should you do with 57, for instance, in this case? That's not clear. Yeah, so for 57 definitely has to be on the right from 55. But if 55 becomes the root, that means 57 should go on the left from 67. It's not clear. It's much more difficult to do. And that's what we'll be talking about next time. Okay, hope you guys enjoyed that. I'll see you next time. Bye.